Hi, I'm Nikki Bradley. This is a video about how to interpret statistics for clinical applications for evidence-based practice. So this is going to be quite a basic introduction to statistics, but we're going to try and cut through some of the complexity and simplify it so that we can get to meaningful figures that we can use in clinical practice.
Let's start with descriptive statistics. We will work our way on to inferential statistics, but descriptive statistics basically describe a data set. So an example might be the number of ACPs within the departments of a trust who are nurses. Just an example, or could be pharmacists or physiotherapists. It's a frequency distribution of nurses working as ACPs. So descriptive statistics explore the central tendency within a frequency distribution. In other words, the mid-range within a frequency distribution. If we're talking about mid-ranges, we have three possible figures. Mode is the most frequent number or value. So thinking about our example, that could be 4 nurses within many of the departments that were looked at. So 4 nurses within the many departments is the most common scenario. It is the mode, the most frequent number or value. Median is the middle number if the results, the values, are written in order. So there you can see an example that starts at 2, works its way up to 7. Okay, there are 5 numbers there. The central number, because when they're in order, is 4. So 4 is the median in the center of those 5 numbers. So 4 is our median. Mean simply means the average. And we know how to work out averages. You add all the values up and then you divide them by the number of values that you have. So in our example here, you add up all those values and then you divide by the number of departments that you've tested. And that gives us the average, or in statistics terms, that's called the mean. In a symmetrical distribution, all of these 3 figures fall at the same point. In the center there, you can see a symmetrical distribution. It's classically described as a bell-shaped curve. A symmetrical distribution is known as a normal distribution. And you can see that the mean, median, and mode all fall more or less at the same point. On either side, you can see variations. These are skewed distributions. Don't worry too much about those, we will come back to them. But in a skewed distribution, those 3 figures do not fall at the same point. Descriptive statistics, apart from exploring this central tendency and the distribution itself, it explores that distribution in terms of the spread of results. So how spread out, how wide-ranging the values that we get are. And that is going to impact on the shape of our bell curve. If we have narrow ranging, we're going to have a very tall bell curve. We'll have a flatter one. If they're wide ranging, that curve will spread out. around the central tendency. You may have heard of standard deviations. Standard deviations give the dispersal or spread of the results in a normal distribution. The standard deviation tells us how wide our range is and how many of the results are close to the mean in a normal distribution. There you can see the mean in the center of that bell-shaped normal distribution. So it's the difference in the result from the mean at that point in the distribution. And the standard deviation spread out either side of the mean. So we can have -1 standard deviation and +1 standard deviation, either side of that mean. We can have -2 standard deviations and +2 standard deviations, either side of the mean, but only in a normal distribution. -1 standard deviation through to +1 standard deviation always comes to approximately 68% of the results. Obviously, you can work out there it's actually 68.2, isn't it? But we call it 68% of the results within -1 and +1 standard deviations. How about -2 and +2? -2 and +2 standard deviations gives us 95% of the results. So always 95% of the results will be encompassed by -2 standard deviations through to +2 standard deviations, either side of the mean. So, okay, what does this mean in terms of the results? Well, what we can tell is that the larger the standard deviation, the larger the spread of results. What also tends to happen is the larger the sample, the smaller the standard deviation. Okay, so if you remember, our ±2 standard deviation either side of the mean gave us 95% of our results. If we look at that in a smaller sample with large standard deviations, you can see there the yellow arrow indicating that -2 to +2 standard deviations with 95% of the results. Let's compare that to a larger sample where the distribution is narrower, so we've got a narrower bell-shaped curve, which means that the standard deviations are also narrower. So in the one on the left, 95% is a much shorter double-ended arrow, isn't it? From -2 to +2 standard deviations. If we compare those two arrows, just to prove to you that it's not an optical illusion, the one on the left is much shorter. So our range between those standard deviations is going to be much narrower. So this 95% of the results between -2 standard deviations and +2 standard deviations gives us what's called the 95% confidence interval. We can be 95% confident that the normal true population mean falls within that range. So the 95% confidence interval is therefore the range of results between -2 and +2 standard deviations. Hence, it's quoted as two figures. So you will see CI for confidence interval 0.67 to 2.81. In other words, -2 standard deviations was 0.67 and +2 standard deviations was 2.81. Our mean, our average was slap bang between the two. The narrower the confidence interval, the narrower the distribution is. Because remember, we said those standard deviations get narrower, the range between them gets narrower, the narrower the distribution. A narrow confidence interval gives the study power because the sample has probably been large enough to be sure that the researchers have captured the true population mean. So a narrow confidence interval is a good thing. This suggests that the study accurately reflects what would happen if you went out and you managed to test the whole population. So in other words, it's saying that this is most likely representative of the true population. Hence the word power. It has the power to be generalizable to the entire population. So that was confidence intervals. Confidence intervals give us an idea of the power of the study. So what about p-values? You may have heard of p-values. You may have seen them quoted next to statistics. P equals. The P stands for probability. What we're talking about is the probability of obtaining a test statistic, in other words, that numerical result that it's attached to, purely by chance. Most researchers apply a 5% p-value. Basically, what you need to know is that if the p-value is greater than 0.05, so greater than that 5%, the results are not statistically significant. And the treatment outcome, or the outcomes of that, giving that treatment, is likely to be due to chance. So what we're looking for is a p-value that is less than 0.05. What it's actually saying is that if the p-value is greater than 0.05, the likelihood that the results were due to chance is greater than 1 in 20. And this is not good statistically. If the p-value is greater than 0.10, the likelihood that the results were due to chance is greater than 1 in 10. So that's really definitely not good. The p-value you will see stated after a test statistic that it relates to in the format of p equals whatever the figure is, 0 point something. So if we've got 0.07, is that good or not good? Is it greater than 0.05? It is, isn't it? So therefore, the results that that's attached to are not statistically significant. There is an unacceptable risk that that statistic was due to chance. So, okay, let's look at some good p-values. Good p-values indicate that the results are statistically significant. So let's look at these. So we said about 0.05, that's the 5% p-value. What that represents is that there's a 1 in 20 chance that those results were just down to chance alone. Let's go up the way, if you like, to our 1% p-value, which is 0.01. So obviously that's less than 0.05. It's a 1% p-value. That means that there's a 1 in 100 risk probability that these results were due to chance alone. So you can see that's actually quite a small probability that the results were due to chance. Going even smaller, if you have a 0.001 p-value, it's a 0.1%. In other words, 1 in 1,000 probability that the results were due to chance alone. So if you were a researcher, you'd be very, very happy with a p-value at 0.001. That would mean that your results were strongly statistically significant. So strongly significant results may have a p-value at the 1%, which is 0.01, or even 0.1%, which is 0.001 level. So, okay, what about these? Let's go through some. P equals 0.01. Well, we've got that one over on the left, haven't we? It's an easy one to start with. There is a 1 in 100 probability that these results were due to chance alone. Is it less than 0.05 is what we're really interested in? And of course, yes, it is. 1 is less than 5. So that is strongly significant. P equals 0.04. Is that less than 0.05? It is, isn't it? So therefore, those results are significant. P equals 0.08. Is that less than 0.05? No, of course it's not. Therefore, those results are not statistically significant. There is an unacceptable chance that that result was due to chance alone. P equals 0.001. Yes, of course, we've got that on the left there, haven't we? That is a 1 in 1,000 chance, that probability that those results were due to chance alone. So therefore, we would say this is very strongly significant. We might just say strongly significant. Okay, P equals 0.14. Is that more than 0.05 or less? It's more, isn't it? It's greater than 0.05. Therefore, these results are most definitely not significant. So again, this brings us on to the difference between statistical and clinical significance, and they are most definitely not the same thing. So remember, the confidence interval tells us that we can be 95% confident that the true population mean, in other words, if we tested everyone in the population, it would fall between those two figures. And we learnt that a p-value that is less than 0.05 gives us a result that is statistically significant. But what if that range, that confidence interval, doesn't include a figure that is really clinically significant? Okay, so let's look at an example. In a study looking at antibiotics for shortening the duration of bacterial tonsillitis, the 95% confidence interval measured in hours is 2.3 to 6.6. The p-value is 0.02. So that is less than 0.05, therefore it is statistically significant. And there we've got our confidence interval in hours. Our average is between 2.3 and 6.6 hours. So what that's telling us is, although the value, the test statistic, is statistically significant, the antibiotic will only reduce the duration by 2.3 to 6.6 hours. 6.6 hours, of course, being our +2 standard deviations. That encompasses 95% of our results. So 95% of the people tested reduced the duration of their symptoms by 2.3 to 6.6 hours, the best being 6.6 hours within that 95% confidence interval. Do we actually think that that is clinically significant? Is it worth giving that antibiotic for a maximum reduction of 6.6 hours in the symptoms at that cost with the risk of side effects? Probably not. So therefore, even though it's statistically significant, the actual confidence interval shows us that the range, 95% of the results fall in a range that really is not that good. So therefore, and most good researchers do, the confidence interval should be stated and interpreted alongside the p-value. So it's okay looking at the p-value saying, oh, statistically significant, that's great. This antibiotic works against bacterial tonsillitis. But actually what the confidence interval is telling us is that the improvement is really quite marginal in the grand scheme of things. And I promise to come back to skewed distributions. As I said, not all distributions are normal. In other words, not all of them are a nice symmetrical bell curve. Many are. If you tested IQ, heights, various other things, generally they come up as a symmetrical, i.e. normal distribution. So many measurements do have a normal distribution and form that bell-shaped curve. So what that tells us that the majority of results will be fairly similar, fairly close to the mean, the average, with a few extreme measurements either side of the mean. So as I said, if you measured heights of students in a university, as long as it's not a university that has a very large baseball team, for example, or if you measured IQ. IQ is classically a bell-shaped curve. Sometimes we don't get this, and this is where we have the skewed distributions that I showed you earlier. So we can have, you don't have to really remember this positive and negative skew, but if you look at the symmetrical distribution in the middle, you can see that these are not symmetrical. And as we said before, in these circumstances, the mean, median, and mode are different. They don't fall at the same place. So in a skewed distribution, the mean and mode are different. The significance really of this is that different statistical tests have to be used if the distribution is skewed. And these are known as non-parametric tests. Parametric tests are used with a normal distribution. Non-parametric tests, so a different set of tests, have to be used with skewed distributions. So an example of a common non-parametric test is a Mann-Whitney test or a Mann-Whitney-U test. If you see that used, you know the distribution was skewed. If you see t-test, then this is a parametric test. It's only used in symmetrical distributions, so it should not be used if the results are skewed. So in this case, in a skewed distribution, you don't use the mean, you use the median. And you don't use standard deviations, you use something called the interquartile range. So, okay, remember the median. The median is the middle number if the values are written in order. Remember our previous example where we had 4 as the median in a set of 5 figures. So those 5 figures started at 2, ended at 7. Right slap bang in the middle of this sequence of numbers, we had 4. So the interquartile range includes 50% of values with the median in the center. And you can see, unlike standard deviations, and because we've got this skewed curve, then there's going to be a difference in width between the median and quartile 1 and the median and quartile 3. But that is the interquartile range. Which brings us on to inferential statistics. Inferential statistics are used to test hypotheses. So what the researchers do is use the data to make inferences or predictions about a larger population. A hypothesis is a prediction of the relationship between two variables. So we're not looking at descriptive statistics where we're looking at sort of really the predominance, the prevalence, the distribution of a certain thing. What we're looking at here is two variables, sometimes more, and we're looking at a relationship between those variables. And remember, we've talked about independent and dependent variables. The independent is the cause or the intervention or the event. The dependent variable is the outcome or effect of the independent variable. So you might hypothesize that using a certain treatment reduces recovery time or reduces mortality risk. For example, you might say that remdesivir reduces mortality in coronavirus. Rather a topical one there. But actually, the researchers don't test that hypothesis. It's known as the alternative hypothesis. What they test is the null hypothesis. So they will test that remdesivir does not reduce mortality in coronavirus. In this case, the independent variable, of course, our cause or intervention, is remdesivir. The dependent variable is reduced mortality. So by testing a reasonably sized sample of patients and looking at the outcome, as long as you control for all those confounding variables, remember, you can infer that similar patients in comparable situations would have a similar outcome. The type of test that researchers choose to use depends on various things. Depends on the number of variables being tested, what type of variable or categorization of variable they're testing, and various other factors. There are whole tables suggesting appropriate tests for different situations, different combinations of variables. Most researchers use software such as SPSS, and this will also give them an indication of the distribution, the p-value, and the confidence interval. So you decide what test you're going to do, you load all your values into SPSS, all your results, and then click a few buttons to do your test of choice. SPSS will then produce graphs, it will produce tables, it will produce the figures for you. For normally distributed, in other words, symmetrical distributions, with sample groups that are larger, in other words, more like 30 plus, parametric tests are used. And examples of parametric tests that may be used are paired or unpaired t-tests, sometimes called a student t-test, Pearson correlations, or one-way ANOVAs, which involve a comparison of variance. For skewed distributions or smaller sample groups, non-parametric tests are used. And we've already mentioned the Mann-Whitney test, Mann-Whitney U-test. There's also a Kruskal-Wallis test, a Wilcoxon test, and a Spearman correlation. These are just examples. Other tests most definitely are available. At this stage, you don't need, you'll be glad to hear, to be able to interpret the figure for each of the tests. But you do need to note the p-value. So remember, this is about statistical significance, not clinical significance, and it's about the probability that those results were due to chance. So a p-value that is less than 0.05 indicates that the result is statistically significant. The confidence interval, if you remember, should be quoted, and it tells us a couple of things really. It tells us if it's a narrow confidence interval, the study has greater power because there was a greater sample to produce that narrow confidence interval. It also gives us an idea about clinical significance because you can look at the range to see what the -2 standard deviation, the +2 standard deviation were, and within that, is there a result that you really think is clinically beneficial? And as promised, numbers needed to treat, NNT, gives a simple interpretation. What it's telling you is how many people you have to treat for one person to benefit. So therefore, it not only really demonstrates the efficacy of a treatment, but if you know the cost of that treatment, it can also predict costs in relation to efficacy. You'll be pleased to know there are online calculators that can work out numbers needed to treat for you. The simplest is ClinCalc. The URL is there, and I would suggest you perhaps bookmark that so you can find it easily. Others require you to enter more information, such as CalcTool. So CalcTool asks you to enter information regarding event rates, which we'll talk about in a minute. So to understand the basics of numbers needed to treat, really, you do need to understand some terminology. Event rates, then. The event rate is the percentage of people experiencing an event, whether that event be good, bad, or indifferent, in either the treatment group, in which case it's the experimental event rate, or in the control group, known as the control event rate. So, in other words, X% of each group have or do something. It's calculated by dividing the number of people in the group with the number experiencing the event. So, simple example, if 12 of you have blue eyes and there are 33 of you in the class, then we take that 12 and we divide by the numbers in the class. So 12 divided by 33 is 0.36. So 0.36 of you have blue eyes. Doesn't really mean a lot, but if we put it into a percentage, then it's slightly more meaningful. So in a percentage, of course, what we do is we take that 0.36 times it by 100, which would give us 36%. So in other words, that simple calculation is just telling us that 36% of the class have blue eyes. And often in research papers, they will do this work for you, and they will tell you that X% within a group had whatever, did whatever. This that they're quoting is the event rate for that group. It's the number of people within a group who experienced an event. In the case of our eye colour, 36% in a class of 33 had blue eyes. absolute risk reduction, ARR, you need to deduct those event rates from another. So you need to take the experimental group event rate and take that away from the control group event rate. So ARR, absolute risk reduction, equals CER, control event rate, minus EER, experimental event rate. So obviously you have to get your event rates first. CER minus EER equals ARR. But in this case, because it is risk reduction that we're talking about, clues in the name, absolute risk reduction, the event rates that we need to use have to reflect the adverse event. Obviously, we're not going to use our blue eyes because that's not really adverse, not having blue eyes. So, okay, let's try another example. In a study of streptokinase post-MI, in the control group, 88% of patients survive for 5 weeks. Well, that's not an adverse event, is it? What is adverse is the 12% that died. So 12% die. If we put that into a decimal, we're looking at 0.12. In the experimental group, 90.8% survive for 5 weeks. Again, that's not an adverse event rate. We need the opposite. So the difference, obviously, between 90.8% and 100% is 9.2%. So 92.2% of them must have not survived. In other words, they died. As a decimal, that's quoted as 0.092. So here we're focusing on the adverse event, people who died as opposed to people who survived. So our absolute risk reduction would be, remember it's our control event rate, which was 0.12, minus our experimental event rate, which was 0.092. If we work that out, it comes out as 0.028. Put it back up to a percentage to make it a bit more understandable, and we've actually got 2.8%. So in other words, we can interpret this in words as there is a 2.8% risk reduction in death in people treated with streptokinase post-MI. Remember, absolute risk reduction is all about risk reduction. Therefore, the event rates are the adverse event. CER minus EER. So, is that good? 2.8. Now we've got our ARR, we can calculate it as numbers needed to treat, which is a really simple calculation of 1 divided by absolute risk reduction, the ARR. So if we do that, if we take 1 divided by 0.028, that's our 2.8% back into a decimal, equals 35.71. What we're talking about here is 35.71 people. Obviously, we can't have 0.71 of a person, and even if it had come out as 35.1, we always round it up. So, of course, rounded up, we're going to get 36 people. So what we're saying here is that we would have to give 36 people streptokinase to stop one person from dying within 5 weeks of their MI. So numbers needed to treat is the number of people we need to treat for one person to benefit, remember. So in the terms of this study, 36 people would have to be treated with streptokinase to stop one patient from dying within 5 weeks of their MI. Okay, so that begs a few questions, doesn't it? 36 people is quite a lot to stop one person from dying. But what if that treatment was cheap? It's not much of a financial consideration for the chance of someone living. What about if it was expensive? That's quite a lot of money for one person to not die. What if it has significant side effects? We've got all these people having nasty side effects for the sake of one person not dying. So we can start to make value judgments around that figure because it's quite meaningful. Okay, I have to treat X number of people for one person to benefit. Obviously, if that's a low number of people I need to treat, then that's great. If it's a high number of people I need to treat for one person to benefit, I need to look at other factors involved here. Maybe it was difficult to administer. The other thing is, how does that then compare to other treatments or to an existing treatment in terms of cost, potential side effects, or practical issues? We'd need to work out the numbers needed to treat for the comparisons, and then we'd get an idea of what's going to be the better option. So a low numbers needed to treat is a good thing. It's a positive result. Imagine we had a numbers needed to treat of 1. That would mean that we would have to treat one person for one person to benefit. In other words, everyone would benefit. If our NNT was 2, that would mean we'd have to treat 2 people for one person to benefit. In other words, 50% benefited. 4 would represent 25% and so on. So in numbers needed to treat, a low figure is a good thing. In numbers needed to harm, though, although it's calculated in exactly the same way, so we have 1 divided by the absolute risk reduction to calculate it. In this case, large numbers are better. So think about it. What we're saying is that we would have to treat 50 people for one person to be harmed, whereas if we said we had to treat 3 people for one person to be harmed, obviously treating 50 is a lot better because we're talking about harm. So calculated in the same way, but here we want large numbers. Numbers needed to screen is another one that can be used. It's also calculated as 1 divided by ARR. What it represents is the number of people screened to prevent one death. So obviously in this case, low numbers like NNT are going to be better. We screen fewer people to save one, rather than screening lots of people to save one.
So you can't deny statistics are quite complex. And to some extent, we do have to trust to the researchers, especially if that article is peer-reviewed. But recognizing the p-value and whether a statistic is due to chance or it's statistically significant can be important. Also having an appreciation of that confidence interval. How powerful was this study? How big was the group? How narrow is that confidence interval? And then we went on to look at numbers needed to treat, numbers needed to harm, or numbers needed to screen. And this is where really it starts to get more clinically significant. Obviously, you have to then interpret that in terms of cost, resources, and compare it to perhaps established treatments. But it gives you a good idea in a simple term that is understandable for all. So with these skills, you can interpret the statistical results sufficiently for most clinical applications. Thank you for watching, and I'll see you soon.